Today I'm going to explain a current phenomenon and how scientists are going to get around that. Due to the observable universe's expansion, older and farther away galaxies are becoming harder to see with telescopes. Because the light from these galaxies are so far away, their light is stretched to an infrared wavelength. The Hubble is unable to detect these billions of galaxies in that wavelength. Fortunately, for years, scientists have been designing and manufacturing the James Webb Space Telescope. Only recently was the instrument attached to the frame of the telescope, which means there's still a lot of work to be done until the 2018 launch at the Lagrange Point 2. This is the James Webb Space Telescope. It will be the largest space telescope ever built, and its design and function is very intricate. Let's talk about the mirrors first. Unlike the one large mirror that Hubble has, James Webb has 18 hexagonal mirrors made from beryllium and coated with a super thin sheet of gold, since gold is the best material for picking up infrared light. There is then a secondary mirror that bounces the light from the 18 mirrors to the instruments in the telescope to be more focused. The James Webb Telescope has several different parts to its instruments. The first is the ISIM, which houses the three major components. The next is the NIC, or the near-infrared camera. This is what detects the infrared light we want to see. From there on, the light is dispersed from an object into a spectrum with the NIS, or the near-infrared spectrograph. Analyzing the spectrum of an object can tell us about its physical properties, including temperature, mass, and chemical composition. However, there are more than one set of spectrographs and cameras for this telescope. There are other components for different parts of the spectrum, like the MIS, or the mid-infrared spectrograph. The last component is a guidance system which keeps the James Webb on course. The important parts of the telescope are protected by a super thin heat shield. This allows one side to operate at extreme cold temperatures, and the other side to operate at really high temperatures. The instrument and mirror need to be cold so other heat sources don't screw with the infrared system. The solar panel, however, can and will get hot. The whole telescope is run on an internal battery, which is the primary power source until the solar panel is activated. Once that is up, it becomes the only source of energy. In this process, the photovoltaic, or solar panel, converts the sunlight into electrical energy that is used to power the instruments, which detect and send information on the telescope.